Hello and welcome once again to the Aakash BYJU'S YouTube channel. My name is Atiullah and we are live once again with JEE Mission 2022, and on agenda this time is semiconductors and electronic devices. So guys, very warm welcome. Before we begin, just let me know if you can see me clearly and you can hear me properly so that we can quickly get started with this session. Alright, so people coming in: Rishabh, Shreya, Martin, Jyoti, a very good evening. Ahmed, Medansh, very good evening guys. So good to have you here, and this is going to be a very important session. So just quickly give me a thumbs up so that we can proceed with the session. Tanu Singh, very good evening. Alright, a lot of people have joined. Hello Anshul, how is it going? Alright, so I hope you can see me properly and hear me clearly. Alright guys, so let's get started. Okay, so we are talking about semiconductors and electronic devices. This is a very neglected chapter, but let me tell you, it is a very important chapter from JEE standpoint. Expect at least 1 to 2 questions in JEE Main for sure. Okay, and oftentimes it is a topic which is not very well understood, which is very different from all that we have studied in physics so far. So it might happen that this is something which is not very clear, things are not very conceptually clear, but no problem, I'm here to make that clarity, to give you that clarity for this topic here. Okay, so we generally do a lot of questions, we do numericals, but in this session, because it is semiconductors, and the most important part of semiconductors is the theory. If you understand the theory well, you can answer theoretical questions, and also you can solve numericals, because numericals are very basic. So we are going to focus our energy on understanding the concepts. So this is going to be a purely theory session. Okay, alright guys, a lot of people have joined in, so it's going to be a very important session, and I'm going to pick some important topics of the chapter, topics like band theory of solids, the p-n junction, okay, that forms the base of semiconductors, and I'm going to invest a good amount of time on transistors, because transistors is something which a lot of people have problem with. Okay, when I was studying, even I had a lot of problem with transistors because it is a very different topic. All right, all set? So yes, we are all ready to get started with this session. Okay, and we are live, so make use of it. If there's something you don't understand, ask away. Okay, don't be shy, ask me and I'll try my best to answer all of you. All right, perfect, great. So let's get started with this session. All right, start. So first I'm going to start with band theory of solids, the most fundamental thing. Now when atoms are far apart, okay, atoms of the same element are very far apart, okay, then the energy level of the electrons corresponding to their quantum state is going to be the same, okay, isn't it? Okay, for example, let's take the example of silicon 14. So the electronic configuration for silicon 14 is something like this, and the valence electrons have an electronic configuration of 3s2 3p2. Okay, now when we bring atoms close to each other, okay, when we are bringing these atoms close to each other, the electrons and the nucleus of other atoms, they interact with each other. So what is the result of that? So let's say there are n atoms, okay, and let's talk about L is equal to 0, which means the S shell. So in the S shell, there can be 2 states, there can be 2 electrons, which means there can be 2 states. Now when we are talking about n atoms, then there are 2n states, okay, and both those states are filled for silicon. So there are 2n electrons. Now notice that all those 2n states have the same energy level when they are isolated. Similarly, for the p shell, okay, there can be 6 vacancies. Okay, so there can be 6 states for the p orbital, and if there are n atoms, then there can be 6n states. But how many are filled up? 1 and 2, only 2 are filled up. So how many electrons are there? There are 2n electrons for the p shell. Okay, now you can notice that for all these 6n states, the energy level is the same because the atoms are isolated, they are far away. But as we go from right to left, and from right to left, what we are doing? We are decreasing the distance. When we are decreasing the distance, then all these discrete energy levels, they are going to merge into each other, and then finally they are going to become energy bands. So there is the lower band, okay, So what happens is that there are going to be 4 n states in the lower energy band, and there are going to be 4 n states in the upper energy band or a higher energy band. Okay, so there were 2 n electrons there were 2 n states in the lower energy level, and there were 6 n states in the upper energy level. Okay, but when they have merged together, there have been 2 bands that are formed, and in the lower band there are 4 n states, and in the upper band there are 4 n states. Now if we are talking about temperature at 0 Kelvin, absolute 0, okay, no energy at all, we are not giving any energy, so all those 4 n electrons are going to reside in the lower energy band, which we call the valence band. Okay, this region, we are talking about this region, this is called the valence band, and the upper band is called the conduction band. Okay, when we give energy to these electrons, they can jump to the conduction band, and you can see that there is an energy difference between the two bands, and this is called the energy gap. Is that correct? Okay, so in a nutshell, what happens when atoms are brought together, the discrete energy levels merge into each other and they form energy bands. The upper energy band is called the conduction band, the lower energy band is called the valence band, and there is an energy gap between them. Is that correct? Perfect. So what is the result of that? Now what does valence band mean? Okay, so when we have this silicon semiconductor, okay, now these atoms are in covalent bond, so the electrons are bonded in covalent bond. This state of the electrons is called the valence band. Okay, simply it means that all these electrons are bonded to their covalent bond, and they are in the lower energy level, hence we call it the valence band, because the valence bonded electrons are over there. Is that correct? Okay, now the valence band will be entirely occupied by the electrons because we are not giving any energy. But if we provide energy, then these electrons can break off from their covalent bond, and when they break off, they can become free, and when they become free, they can move around, and when they move around, that if electrons or if charge carriers are able to move around, we can say that they are able to conduct, hence they go into the conduction band. Is that correct? Okay, so they are going to become free from their bond and they are going to go into the conduction band, and the energy difference between this energy and this energy is called the energy gap. Okay, and this is also called the forbidden energy gap because the electron cannot be in the forbidden energy gap. It is either going to be in the valence band or it is going to be in the conduction band. Is that correct? Any problem so far? Okay, so we understand the meaning of what is conduction band, what is the valence band, and what is the energy gap. Okay, I hope we are clear so far. Now this band gap or this energy gap determines whether an element is going to be a conductor, a semiconductor, or an insulator. So in case of conductors, the conduction band and the valence band are overlapping. Okay, so very easily an electron can go from the valence band to the conduction band, hence the conductivity is very high. But for insulators, the energy gap is very high. It is greater than 3 electron volt. For something like diamond, the energy gap is 6 electron volt. So this acts as an insulator because you have to give a lot of energy for them to go from the valence band to the conduction band, which is not feasible. And then in between we have something called semiconductors. Okay, so for semiconductors, the forbidden energy gap is less than 3 electron volt. If no energy is supplied, the electrons are going to sit in the valence band. But if energy is provided, a little amount of energy is provided, they can go into the conduction band and the conduction of the material is going to increase. Is that correct? Alright, so this is how we classify conductors, semiconductors, and insulators, and the mystery or the reason is simply the energy gap. Is that correct? Alright, so for silicon, you have to provide an energy of 1.1 electron volt. The energy gap is 1.1 electron volt. So if we provide 1.1 electron volt to the electron, then it is going to go from the valence band to the conduction band. And for germanium, it's lower because germanium is larger in size. So it is 0.72 electron volt. Okay, so this is basically the band theory of solids in a nutshell. Alright, now we talk about types of semiconductors. Okay, there are 2 types of semiconductors. We know there is an intrinsic semiconductor and there is an extrinsic semiconductor. So first we are going to talk about the intrinsic semiconductor. Okay, so let's take an example of silicon or germanium. It could be any element which has 4 valence electrons. So it could either be silicon, germanium, okay, just to give you an example. Now what you see here is that these are bonded. Okay, so this is a covalent bond. So these 2 electrons are bonded in a covalent bond. This is a covalent bond. Electrons are bonded in a covalent bond. Okay, now what happens if we provide energy to these electrons? Okay, you can provide energy in many different ways. We can use light to give energy, or we can use heat to give energy, but the idea is to give energy. Now if we give energy, what is going to happen? This covalent bond is going to break, and if this covalent bond breaks, then this electron is going to become free. Now it is free to move. Obviously it is not going to go out of the metal, no, but it is going to become free. Okay, this electron is going to become free to move around in the crystal lattice, which means it will be capable of conducting electricity, and this is known as thermally generated free electron. So we have used heat energy to do that, so it is called thermally generated free electron. Now this electron has become free, it is going to move around, it is going to roam around, and conduction is going to happen. But there is another very important thing here, that there is a hole also created. What is hole? The electron was there, now the electron is not there, so there is a vacancy over there, and when there is a vacancy, this atom will try to fill that vacancy. And how will it fill this vacancy? It can fill this vacancy by an electron which can move from another site to this particular site. Is that correct? Okay, so the electrons can move to fill that gap, to fill that hole. Now practically, in all practical terms, or for all practical purposes, we can understand holes to be positive charges. Actually they are not, they are just lack of negative charge, but we can understand them to be positive charges. So as the electrons keep on filling the holes start moving. Okay, so because of that as well, conduction of electricity takes place. So there are 2 charge carriers in this case. We have not seen ever in current electricity a situation like this. It is unique to semiconductors. We have 2 charge carriers. We have the electron, it moves around and it is going to conduct electricity separately, and we have the hole which is going to move around and it is going to conduct electricity separately. Is that correct? And this is an intrinsic semiconductor, which means all the atoms here are the same. There is no foreign impurity or there is no other substance injected into this semiconductor. Is that correct? Okay, so whenever heat is provided, we create an electron hole pair. Okay, so we create an electron hole pair. The electron have become free, they are free to move, they will conduct electricity, they will contribute to conduction, and the holes, as electrons keep on filling the holes also move, so they also conduct electricity. Is that correct? Alright, so this is the scenario. At 0 Kelvin, all the electrons are going to sit in the valence band, but if we provide energy, if temperature is greater than 0 Kelvin, we provide energy, then electron holes pairs are created and the electron are going to go from the valence band to the conduction band. Is that correct? Any problems so far? Okay, so is this clear? If there is any confusion, do let me know. If you think there is something not clear, you want to ask, please don't hesitate to do that. You can certainly do that. Alright, good so far. Any problem? I hope this is absolutely clear. So what is the property of intrinsic semiconductor? The most important property of intrinsic semiconductor is that Ne is equal to Nh. What is Ne? Ne is the electron concentration and Nh is the hole concentration. Now whenever we have an intrinsic semiconductor, whenever an electron, the thermally generated electron is produced or created, simultaneously a hole is also created. So hole and one electron are simultaneously created. So we have created an electron hole pair. So the number of electrons would be exactly equal to the number of holes. So the concentration of these 2 charge carriers is going to be the same. Is that correct? And we call it Ni, and Ni means the intrinsic carrier concentration. Is that clear? Alright. Now another very important point to note here is that the current is going to be because of both charge carriers, the current due to the electrons plus the current due to the holes. Is that correct? Okay, so we have provided energy, electron hole pairs are generated. Now what also happens is there are recombination of electron and holes. So that is a simultaneous process. Okay, electron hole pairs are generated and electron holes recombine, and this process is called recombination. So that happens simultaneously. So when equilibrium is attained, at equilibrium the rate of generation of electron hole pair will be equal to the rate of recombination. Is that correct? Okay, so this is the equilibrium state. Clear? So this is what an intrinsic semiconductor is. There are going to be a particular number of holes and there is going to be equal number of electrons that are going to contribute to conduction. That is our intrinsic semiconductor. All good? Okay, now can someone tell me what is an extrinsic semiconductor? Okay, can someone throw some light in one line, one or two lines? Can someone tell me what is extrinsic semiconductor? Okay, give it a shot. Tell me if you are following. Tell me if you know this. All right. Okay, so Twinkle Rathore, hi, good evening, a very good evening. Love your enthusiasm. All right. So what is an extrinsic semiconductor? Can someone throw some light on it? Okay, Darun is saying pentavalent impurity. So I'm going to say, Darun, you are half correct. Okay, it could be a pentavalent impurity or it could be a trivalent impurity as well. Okay, so Jyoti is saying impurity is in semiconductor. Awesome, absolutely correct. Okay, so extrinsic semiconductors are semiconductors which come into existence when a small chemical impurity is added. Okay, and this process is called doping. Putting a foreign substance which should not be there is called doping. You guys have watched enough movie and TV series to know what is doping. Don't do that ever. Okay, but for semiconductors, doping is very good. It's very efficient. It's a very good method for increasing the conductivity of a semiconductor. And the material we are adding, the atoms we are adding are called dopant. Okay, so now we are going to understand that what makes it an N-type semiconductor and what makes it a P-type semiconductor. I'm going to tell you what doping is. Don't worry, Twinkle, I'm going to tell you what doping is. That's exactly what we are discussing here. Okay, I'm going to tell you how it is doped and what is the difference it creates. Don't worry, I'm going to tell you. Okay, first let's talk about N-type semiconductor. In an N-type semiconductor, we add a pentavalent impurity. Okay, pentavalent impurity could be phosphorus, arsenic. It should have 5 electrons in the outer shell. And when we do that, what happens is that the concentration of electrons becomes much greater than the concentration of holes. Correct? And in a P-type semiconductor, what do? We add a trivalent impurity. Okay, trivalent impurity could be boron, it could be aluminum, it could be indium, and in that case the number of holes, the concentration of holes becomes much greater than the concentration of electrons. Okay, so this is the two types of impurities or two types of dopants. Okay, if we are adding a pentavalent impurity, we are going to get an N-type semiconductor, and I'm going to explain the mechanism of N-type semiconductor, don't worry. And when we are adding a trivalent impurity, we get a P-type semiconductor. Okay, so now let's understand the mechanism. So here we have a silicon lattice. Okay, silicon atoms are bonded in their covalent bond. Perfect, very nice. Now we bring in this impurity. Now this is phosphorus. Okay, so phosphorus has 5 electrons in the outermost shell. Okay, so what is going to happen? Now this is going to replace a silicon atom in the lattice. Okay, so it has replaced a silicon atom in the lattice. Now it has 5 electrons. Now 4 electrons have bonded with the other 4 electrons of the silicon atoms. Okay, but this one electron, it is not in a covalent bond. It is just bonded to the nucleus. And because it is just bonded to the nucleus, the attraction is not very high. This bonding is not very high. This bonding can be easily broken. Okay, and we are going to exactly see how. So in this case, what happens is that this is the donor level. Okay, so these electron on the energy spectrum, where are these electrons? These electrons are in the donor level, and you can see that the donor level is just below the conduction band. Okay, the energy of this donor level is just below the conduction band, meaning even if we give it a small amount of energy, all these electrons are very readily going to go into the conduction band. Hence, we are going to have a very high concentration of charge carriers. And what kind of charge carriers? We'll have electrons at the charge carriers. Electrons are going to become the majority charge carriers, and hence we call it an N-type semiconductor, because the majority charge carriers are negatively charged. Is that correct? Okay, so if we look at this closely, how much energy is required? So for these electrons, the energy required is only 0.01 electron volt for germanium and 0.05 electron volt for silicon. Such a small amount of energy. Compare this with energy gap. Okay, so if we had an intrinsic semiconductor, then in order to send an electron from the valence band to the conduction band, we had to give this high amount of energy. But now with an impurity, aluminum as impurity, which has one extra electron, we just have to give this small amount of energy for it to become free, free from the aluminum atom. Is that correct? So we'll have a very high concentration of electrons, we'll have a very high concentration of negative charge carriers. Is that correct? Okay, so this is the idea behind the N-type semiconductor. Is that clear? Now one thing we should note is that the N-type semiconductor is electrically neutral, because it is coming with an extra electron, but it has an extra proton as well. Okay, phosphorus atom will have extra protons also. Okay, so all in all, it is still going to remain neutral. Is that correct? Any problems so far? Okay, are we clear with the N-type semiconductor? All right, so I hope Twinkle, it's clear. I'm glad you understand that. All right, so any problem so far with the N-type semiconductor? I hope this is clear, absolutely clear. Okay, so I'm again emphasizing on this point that the semiconductor, be it an extrinsic semiconductor, it is still going to be electrically neutral. Correct? All right, let's move forward. Now you can guess what is going to happen for a p-type semiconductor. So we have brought in aluminium. Okay, we have brought in aluminium. I'm sorry, did I use aluminium in the previous case? Okay, so if I did, I'm sorry. The atom is going to be pentavalent, so it could be phosphorus, it could be arsenic. If I used aluminium, I'm sorry. Aluminium we are going to use to create p-type semiconductor. Okay, it is trivalent. Okay, now if we use a trivalent impurity, what is going to happen? It is going to replace a silicon atom, and if it replaces a silicon atom, now three electrons are going to get bonded. 1, 2, 3. These three electrons are bonded, but there is vacancy for this hole. Okay, there is a hole over there. So this is not in a covalent bond. So there is a vacancy which is existing over there. Okay, so what does it carry? It carries a hole. Okay, and if it carries a hole, then electrons from other bonds can very readily jump into this hole, which means holes would be created. Holes will become the concentration of holes is going to increase, and the concentration of charge carriers as holes is going to increase. Okay, now what about the energy level? Okay, now all these electrons are in the valence band. Okay, all these electrons are in the valence band. Okay, now this is the acceptor level. Okay, acceptor level means the energy level of this vacancy. The energy level of this vacancy is just above the valence band. Okay, it is very, very close to the valence band, which means if you provide a little bit of energy, then any electron from bonded atom, and any electron which is present in a bond can break free from there and jump into this hole, which means holes will start moving. Is that correct? So you need very small amount of energy for these electrons in the valence band to jump into this acceptor level, and once they have jumped into this acceptor level, holes are going to become mobile and holes are going to move and conduction is going to increase. So in this case, what is going to happen? In this case, we are going to have a very high concentration of holes, and that is why we call it a p-type semiconductor, because the majority charge carrier is going to become positively charged, which are the holes. Is that correct? Okay, now if we look at this closely, again the energy required to go from the valence band to this acceptor level is very, very small. Okay, if it has to go from the valence band to the conduction band, you need high energy. But in this case, to go from the valence band to the acceptor level, it requires very small amount of energy. That is why we are going to have a very, very high concentration of holes. Is that clear? So again, I want to emphasize on it that a p-type semiconductor is also going to be electrically neutral. Okay, so it has one less electron, but will also have one less proton. Is that clear? Okay, Pinky is asking a very good question. If intrinsic semiconductors can conduct electricity, why do we require doping? Now Pinky, understand this, that more the number of charge carriers, more would be the conductivity. Do you agree? More the number of charge carriers, more would be the conductivity. Okay. Now in order to create charge carriers in an intrinsic semiconductor, what is the energy we need? We need this amount of energy. We have to provide this amount of energy. Okay, or let me go back. Yeah, we need to provide this amount of energy to create charge carriers. Okay, to create electron hole pairs. So we have to give more energy to do that. But when we have doped a semiconductor, then in that case we have to give a very small amount of energy to create charge carriers. Okay, so even with small amount of energy, we'll have a lot more charge carriers in an extrinsic semiconductor compared to an intrinsic semiconductor. So to increase the conductivity of the semiconductor, we introduce an impurity or we use doping. Is that clear? Alright, so I hope this is clear. And that is precisely the reason that we use doping. Alright, perfect. Now let's talk about the PN junction, and this is a very, very important topic. It has to be understood well. Okay, let's talk about PN junction. So in a PN junction, what we do is we take a silicon wafer and on one side we introduce impurity such that it becomes p-type, and on the other side we introduce impurity such that it becomes n-type. Okay, so we have a p-type semiconductor and n-type semiconductor, and that is joined together. Okay, now when it is joined together, what happens? Let's understand the mechanism of PN junction. Now on the p side you can see that there are a lot of holes. Now this is an electron and this is a hole. You can see that, okay, clearly in the diagram. So obviously on the p side what we'll have, we have a lot of holes. The number of electrons would be less. On the n side you can see that the number of electrons is much more than the number of holes. So on the p side we have a high concentration of holes, and on the n side we have a high concentration of electrons. Now what is going to happen? Diffusion is going to take place. So from the p side the holes are going to diffuse into n-type, higher concentration of holes to lower concentration of holes, and the electrons are going to diffuse from the n side to the p side. Okay, something like this is going to happen. Watch closely. Okay, something like this is going to happen. Okay, this is called diffusion current. Okay, obviously electrons and holes are moving, charge carriers are moving, so there is electricity. So this is called the diffusion current. Now because of this diffusion, what happens is a depletion region is formed. Okay, what do we mean by depletion region? This region here was electrically neutral, but holes crossed over, which means positive charge is lost. So this side is going to become negatively charged, and on the other side it was also electrically neutral, but electrons have moved to the other side, which means negative charges have been lost, which means this becomes positively charged. Okay, so on the left side, on the p side, we'll have concentration of negative charge, and on the n side we'll have a concentration of positive charge. Is that correct? Okay, so what will be the result? The result would be something like this. So when diffusion takes place, we form a depletion region, and we call it a depletion region because charges are depleted, charges have gone away. Okay, from the p side holes have gone away, and from the n side electrons have gone away, so we call it depletion region. Charges are depleted. So we have a concentration of positive charge on the n side and concentration of negative charge on the p side. Okay, this is called a depletion region. Now because of depletion region, you can understand what is going to happen. There is going to be an electric field. Can you see that? There is going to be electric field from the positive to the negative. And what is this electric field going to do? Think about it. What is this electric field going to do? Now the positive charge is trying to go from p side to n side, and it is going to experience force in the opposite direction. So this electric field will create a hindrance for it to diffuse. Similarly, electrons will try to go from n side to the p side, but the electric field is going to apply a force in the opposite direction. So it is going to restrict, or it is going to inhibit, or it is going to hinder the diffusion of electrons as well. Okay, so what is that? What is this electric field going to do? What is this depletion region going to do? It is going to reduce the diffusion current. Do you agree? It is going to reduce the diffusion current. And also notice that the direction of diffusion current is going to go from P to N. Okay, holes are moving from P to N. Holes are positively charged, so the direction of current is from P to N. And electrons are moving from N to P. Electrons are negatively charged, so the direction of flow of current is going to be from P to N again. So both because of holes and electrons, both because of the diffusions of holes and electrons, the diffusion current is going to be from P to N side. Is that clear? Clear? All good? Perfect. Now there is another very interesting consequence. Okay, what is the consequence? We have created a potential barrier. What does it basically mean? If there is electric field, there is going to be a potential difference between the N side and the P side. Okay, and this is called the potential barrier because it is providing hindrance for the holes and electrons to cross over. It is providing a hindrance to the diffusion current. That is why it is called a potential barrier. Is that correct? Okay. Now there is another very interesting phenomena that is going to happen here. Okay. Now this is electric field. Okay. This is electric field. So if we talk about this hole, which is near the diffusion region, which is near the depletion region, what is going to happen? The electric field is going to apply a force on this hole in this direction. And let's say we have an electron over here. So the electric field is going to apply a force on this electron in this direction. Okay, so because of this electric field, minority charge carrier hole is going to go from the N side to the P side, and minority charge carrier electron is going to go from the P side to the N side. Okay, this process is called the drift current. Okay, this current is called the drift current. Okay, so you can see minority charge carrier hole going from N side to P side, and minority charge carrier electron going from P side to N side. And because of that, the drift current is going to be in this direction. Okay, so the diffusion current is from P side to N side, and there is a current in the opposite direction, which is the drift current from the N side to the P side. Is that correct? Any problem up till now? If there is any problem, do let me know. Is this clear? Is the direction of current clear? Diffusion current is due to the migration or diffusion of majority charge carriers, and drift current is due to the drift of minority charge carriers. Is this clear? Okay, and both these currents are in the opposite direction. Alright, so what is going to happen? In equilibrium, so initially when this depletion region is not formed, only diffusion current will be there, and diffusion current is going to increase. If diffusion current is increasing, the depletion region is going to become larger and larger, and if depletion region is become larger and larger, the diffusion current is going to decrease and the drift current is going to increase. Okay, remember this. The depletion region or the potential barrier, it is a hindrance. It opposes diffusion current, but it supports drift current. Okay, so diffusion current is going to decrease and drift current is going to increase, and finally equilibrium will be attained. Okay, finally equilibrium would be attained. So in steady state, the diffusion current and drift current would be equal, and this is the situation. This is what a PN junction is in a steady state. Pinky is asking, once potential barrier is there, what happens to majority charge carriers? Do they still produce diffusion current? Yes. Okay, so potential barrier is there. Okay, तो potential barrier को ऐसा समझो. Okay, potential barrier को ऐसा समझो कि potential barrier जो है, it is a wall. So you have to cross the wall. Now if the potential barrier is very high, the wall is very high, okay? But if the wall is very high, most of the people would not be able to cross over, but a small number of people can cross over. So a very small number of majority charge carriers would still be able to cross over, okay? So diffusion current would be there, but what is happening in the steady state? In the steady state, the diffusion current and the drift current are going to be equal, okay? So there is going to be no net current flowing, but current is still flowing, diffusion current is still flowing, and drift current is still flowing. Is that clear? Alright, so I hope this is clear. So this is basically a PN junction. Okay, and then what we do is we attach metallic contacts. We attach metallic contacts so that we can connect it to an external circuit. Okay, so now we'll try to understand what happens when we connect it to an external circuit. This is the PN junction in equilibrium. So now we are going to talk about connecting it to an external circuit. Okay, now this PN junction is simply called a diode. Okay, so what is a diode? It is basically a PN junction with metallic contacts. That's all. And this is the symbol for PN junction. Okay, so notice this side. The side on which you have the triangle is the P side, and the side over which you have this bar is called the N side. So this is the symbol, and these are the two terminals. We can connect it to the two terminals of anything, whatever we want. Okay, perfect. Chalo. Now let's talk about forward bias. Okay, what is forward bias? So we have this PN junction and we have not connected it to any battery. So this is the situation. Okay, there is some diffusion current, there is some drift current, equilibrium is there, nothing to worry. But we have not connected it to anything right now. And there is some potential barrier V0. Okay. Now what we are going to do is we are going to attach a battery. Now we have attached a battery in a very specific manner. The positive side of the battery is connected to the P side and the negative side of the battery is connected to the N side. Can you see that? Pinky is asking what is the difference between steady state and equilibrium in this context. They are the same, Pinky, they are the same. Okay, they mean the same thing over here. Okay, now forward biasing means we have connected the positive terminal of the battery to the P side and negative terminal of the battery to the N side. Okay, now what is going to happen? Now because of this, there is going to be an electric field created by the battery in this direction. The electric field is going to go from the P side to the N side. Do you agree? Okay, from the positive to the negative. Now this electric field is in opposite direction to the electric field created by this depletion region. So what is happening? The electric field is going to become smaller, and if the electric field is going to become smaller, then we can see that this potential barrier is going to become smaller. Now the potential barrier has become V0 minus V. This potential barrier has become smaller. Now if the potential barrier has become smaller, what does it mean? Potential barrier, if potential barrier has become smaller, what is going to happen? Potential barrier used to bar what? It used to bar the diffusion current. So obvious hai, what is going to happen? Diffusion current is going to increase. Something like this. The depletion region is going to contract and the diffusion current is going to increase. Can you see that? Can you see the direction of diffusion current? Okay, or let me show it to you. So in this case, diffusion current is going to become much greater than the drift current, okay, because the potential barrier has become lower. So the current is going to flow in this direction. So that's what I have shown to you. Okay, this is the direction of diffusion current. So the net current is going to flow in this direction. Okay, is that clear? From the positive terminal of the battery to the negative terminal of the battery, and inside the PN junction, it is going to go from the P side to the N side. That is the direction of current in forward bias. Is that correct? Clear? So you understand what is forward bias? Okay. Now we want to understand the IV characteristics in forward bias. IV characteristics matlab, if you increase the potential of the battery, then what happens to the current? That's what we need to understand. Okay, so what we have done is positive side connected to P, negative side connected to N. and then we have placed a voltmeter, okay, which will measure the potential difference across the diode, and we have this milliampere which is going to measure the current. Okay, perfect. Chalo, so what is going to happen? Now this is a graph which is going to be created. Okay, now I want you to focus on the voltmeter, ammeter and the graph. Okay, first you focus on this and you tell me what have you observed. Check this out. Check this out. A very nice animation. Lovely animation. Can you see this? Hyper Gaming is asking, sir, is graphs are also important for these biases? Yes. Arey baba, sab to graph mein hi hai. Graph is very important. Yes, definitely. Chalo, watch it again. Watch it again, what happens. Can anyone explain this? Yes, this is forward bias. This is current in forward bias. Can someone explain this to me? I'm going to wait. Okay, can someone explain this to me? Okay, Arjun is asking, sir, कल पेपर है मेरा, फास्ट रिवीजन की ट्रिक बता दो प्लीज. अगर कल एग्जाम है और आज रिवीजन करना है तो just go through your old notes. That's it. That's all. That's all you can do. You can't do much. Okay, so don't worry too much and you just go through your previous notes. You don't have enough time. Ideally, if you had, let's say, a month, I would say solve previous year papers. But abhi ke liye you just revise the previous year notes. Your notes and just try to remember what you already know. All right. So what happens is then when potential is increased, the potential barrier reduces, but the potential barrier is not reduced so much that the current is going to increase. Okay, so initially you can see that from this point to this point, even when voltage is increasing, the current is not increasing. Okay, the potential barrier is not low enough so that a substantial amount of current can flow. But after a point, and you can see that it is about this point, okay, the current increases and it increases very rapidly. This is called the cut-in voltage. This is called the cut-in voltage. Okay, so after this point, which is around 0.7 volt for silicon, the current increases very rapidly. Okay, so think of it like this. Okay, again, potential barrier is a wall. Or let me give you a different example. Let's say something costs 100 rupees. Okay, 100 रुपए दाम है. Okay, so some people will buy it. Okay, it's expensive. It's an expensive thing. Let's say we have a chocolate of 100 rupees. Some people will buy it. Okay, we reduce the cost, make it 50 rupees. Okay, some more people will buy it. We reduce it to 20 people's, more people will buy it. Okay, we reduce it to 1 rupee, a lot of people will buy it. But when we make it zero, okay, when we make it zero, in that case what is going to happen? It is going to be a riot. वहाँ तो भीड़ लग जाएगी. If something you are getting for free, what is going to happen? You are going to go and take it. Okay, so that is what is happening over here. You are reducing the potential barrier, current is increasing slightly, but near the cut-in voltage, what happens? The potential barrier becomes zero. There is no barrier at all. Free में मिल रहा है, तो भीड़ लग गई. So the diffusion becomes very, very high. So the current increases very rapidly. Okay, so this is the nature of the forward bias current. Soumya Brata is saying breakdown voltage. Nahi baba, this is not breakdown voltage. Breakdown voltage reverse bias mein hoga. We'll talk about it now. Okay, now what happens in reverse bias? In reverse bias, we are going to connect the battery in this manner. So positive terminal connected to the N type and negative terminal connected to the P type. In this case, the electric field due to the battery is going to be like this, and the electric field due to the depletion region is like this. So the electric field due to the battery is supporting the electric field due to the depletion region. So electric field will increase. If the electric field increases, then the potential barrier is going to increase further. If the potential barrier is going to increase further, diffusion to ho hi nahi sakta hai. Diffusion is not going to take place, but drift will increase. Okay, drift is going to increase because higher the electric field, higher will be the chance for this hole to be pushed to this side, and higher would be the chance for this electron to be pushed on this side. So drift will increase, diffusion is going to decrease, diffusion is going to become negligible, but the drift is going to increase. When the drift is going to increase, then obviously the current is going to be in what direction? Okay, so this is showing the drift current, this is showing the drift current, and in case of drift current becoming dominant, the direction of current is going to be opposite. Check this out. The direction of current is going to be opposite. Can you see that? So inside the semiconductor, it is going from N to P. The direction of drift is this. The direction of drift current is this. Is that clear? Okay, so in case of reverse bias current, the drift current is going to become dominant. Correct? Okay, so quickly let's talk about the reverse bias characteristic. Let's quickly talk about that. Okay, and I want you to check this out again. It is pretty self-explanatory. Hypergaming is saying in reverse bias units of voltage is also in microampere. No, units of voltage is going to be in volt. Unit of current is going to be in microampere. True. Okay, so check this out. So what happened as the voltage increased, the drift current or the reverse bias current was almost constant. Okay, because the reverse bias constant depends on minority charge carriers, and the concentration of minority charge carriers is small. Okay, so how high is the reverse bias voltage, that does not matter, but what happens is that the reverse bias current depends on the minority charge carrier, and the concentration of minority charge carrier is very low, so the current is dominated by the concentration of minority charge carriers, and hence it is almost constant. So in reverse bias, the current is almost constant, and we have drawn it on the negative side, on the negative I axis, because the direction of current is opposite, and as we increase the voltage at one point, this is going to become, the current is going to become very, very high. Okay, this is called breakdown voltage. The voltage at which the reverse bias current becomes very high is called the breakdown voltage. Okay, and it is called avalanche breakdown. Okay, so I don't have a lot of time to explain avalanche breakdown, but you go back and you revise what is avalanche breakdown. Is that clear? Okay, so if the reverse bias and forward bias current of a PN junction clear. Okay, and what hypergaming pointed out, that the reverse bias current is in microampere because it's very small. It's because of minority charge carriers. Okay, the concentration of minority charge carriers obviously is not very high. So the reverse bias current is typically in microampere and forward bias current is in milliampere. So that's also we should keep in mind. Okay, W Gaming is asking us how reverse bias is used in Zener diodes. Okay, so see, we have limited amount of time. So I wanted to focus on the fundamentals and the core principles. Now the core principles I have already discussed. Okay? Now what you can do is, you can go back and you can from any source just revise Zener diode. Okay, if you understand how reverse bias works, you will understand very easily what is Zener diode. You will understand rectifier circuit. If you understand the forward bias and reverse bias current, you will understand rectifier circuit. If you understand PN junction, you are going to understand optoelectronic devices like photodiode, LED, solar cell. Now you just have to read this. Pick up NCERT. Pick up NCERT. You have the fundamentals. You go ahead and read it. It is going to become very clear to you. Okay. I cannot spend much time on this because obviously we are short on time. So I want to focus more on the problem areas. Okay. And I want to focus more on transistors. Okay. Which I know is a problem area for most of the people. So I want to spend the rest of this session in detail about transistors because it is something which takes a little bit of time to understand. Okay. Alright, so I'm going to give you a few seconds over here before we get into transistors. Let me take a breather. I'll also want to drink water. But in the meanwhile, if you have any questions on the session so far, please let me know. Okay, I'm taking a 5-10 second break just to Catch a breath. How many of you have problems with transistors? Okay, how many of you are not able to understand transistors completely? Let me know. And also let me know how many of you are comfortable in transistors. Do let me know. Alright, so I hope up till this point there is no problem, okay, in this session. Yes, Harshita, I'm going to explain transistors in a lot of depth. Don't worry about that. Okay, Manisha is very comfortable in transistor. That's great. Hyper Gaming is comfortable in transistor. That's great. But still, there's going to be a good revision of transistors. Okay, and if you're facing problem with transistors, then surely this is going to be very helpful. Okay, so let's talk about transistors. Now the difference between transistors and any other device we have seen so far is that transistors have 3 terminals. Okay, all the other devices we have seen have 2 terminals. Battery has 2 terminals, resistance has 2 terminals, capacitor has 2 terminals, inductor has 2 terminals. Okay, but transistor has 3 terminals. Okay, so let's try to understand what is this transistor made up of. Okay, segments of a transistor. So there are 3 segments of a transistor. We have an emitter, we have a base, and we have a collector. So these are 3 semiconductors joined together. One is emitter, one is base, and one is collector. Okay, now they have different functions. So their size and doping levels are also different. So the emitter is moderate in size, but it is very heavily doped, very heavily doped. Okay, the base is the central segment. Okay, this is thin intentionally, and we're going to talk about why it is thin, and it is very lightly doped. That's also something we are going to talk about. And the collector is moderately doped and largest in size. Okay, so the collector is very large in size, so that does not get very heated up, but the doping level frankly of a transistor of a collector does not matter much. Okay, but it is moderately doped. Okay, so let's try to understand that there are 2 kinds of transistors. NPN transistor, where a p-type semiconductor is sandwiched between 2 n-type semiconductors, and there is a PNP transistor where an n-type semiconductor is sandwiched between 2 p-type semiconductors. Now this is the circuit symbol, and just looking at the circuit symbol we can tell what is the type of the transistor. Is it NPN transistor or PNP transistor? So I'm going to tell you a shortcut. Now this arrow over here, this arrow tells me the direction of current from the base to the emitter, or the emitter to the base. Okay, and the only thing you need to remember is that the current is always going to flow from P to N. So if the current is flowing from P to N, then obviously what kind of transistor it is? It is an NPN transistor. This is always the base. So there can be confusion between emitter and collector, but the arrow is going to be either from the emitter or towards the emitter, and the direction of current is always going to go from P to N. So this becomes an NPN transistor. Here the direction of current is like this, so it is going to go from P to N. So this becomes a PNP. This becomes a PNP transistor. Is that clear? Okay, so we should be able to identify the circuit symbol of a transistor. Is that clear? So this is the circuit symbol, and this we have already discussed, that the arrow on the emitter line shows direction of current between the emitter base junction. Is that correct? Clear? Okay. Now in normal operation, emitter base junction is forward biased and collector base junction is reverse biased. Okay, so this is something we call the active state of the transistor, and we are going to talk about different states of the transistor. But in normal operation, the emitter base junction is forward biased and the collector base junction is reverse biased. Okay, chalo, now let's try to understand how does a transistor work. What is the working of a transistor? Okay, so here is the emitter. What does an emitter have? An emitter has a lot of electrons. Okay, the majority charge carrier, it is heavily doped, so the majority charge carrier here are electrons. So it has a lot of electrons. But before that, I want you to appreciate something. What is this VEE doing? What is this VEE doing? Okay. Now between the emitter and base, this is a junction. This is simply a PN junction. This is the emitter base junction. And between the emitter and the collector, there is another junction. Okay. This is the base collector junction. Okay. Now what is this battery VEE doing? The positive terminal is connected to P and the negative terminal is connected to N. What does it mean? It tells me that the emitter base junction is forward biased. Can you see that? The emitter base junction is forward biased, hence the depletion region is thin. Can you appreciate that? Right? And what is this battery VCC doing? Okay, the positive terminal is connected to the N side and the negative terminal is connected to the P side. Okay, so what is this? The base collector junction is reverse biased. Do you agree? The base collector junction here is reverse biased. So this is the normal operation mode. We are going to talk about the active state of the transistor, but in normal operation, this is how we use it. Correct? Okay. Now because the emitter base junction is forward biased, what is going to happen? Diffusion is going to take place. When we have forward bias, what is going to happen? Diffusion is going to take place. So a large number of electrons are going to go into the base. A large number of electrons are going to diffuse into the base. Correct? A large number of electrons have diffused into the base. Okay. Now base is very thin. Okay. Base is very, very thin. If the base is very thin, all these electrons are going to come very close to the base collector junction. Number one. And the second thing is the base is very lightly doped, which means it has very less number of holes. So the chances of recombination are also very low. Correct? Okay. Now when these electrons come very near to the base collector junction, what happens? The base collector junction is reverse biased. So the direction of electric field is going to go from collector to the base, which means there are two things happening over here. All these electrons, okay, they have come into the base, and from there, because the base is very thin, they're going to come very close to the depletion region, and because of this electric field, they are going to go to the collector. They are going to deluge to the collector. Okay, they're going to get flooded towards the collector. Okay, so the majority charge carriers, electrons, are going to go to the base, and most of the electrons are going to go to the collector. Okay, and very few electrons are going to come out from the base. This is the main or you can say this is the crux of the understanding of transistor. Okay, I'm going to say this again. Majority charge carriers, electrons, they flow into, because the emitter base junction is forward biased, they diffuse into the base. When they come into the base is very thin, so all these electrons are very, very near the depletion region, and the base collector junction is reverse biased, so this electric field is going to pull these electrons and throw it into the collector. Okay, and also because the base is very lightly doped, the chances of recombination are very small. So in effect, what is going to happen? Most of the electrons which have come into the base are going to go to the collector, and very few electrons are going to come from this terminal of the base. Is that clear? Is this clear? Hypergaming is saying that's why its name is collector. Absolutely, absolutely. It is going to collect those majority charge carriers. Okay. In a transistor, forward bias is very small as compared to reverse bias. Ye kyun hota hai, sir? I'll explain that to you. Okay, I'll explain that to you. Don't worry. I'll certainly explain that to you. Okay. Now, if this is clear that most of the electrons which reach the base, most of them go to the emitter and some of them are going to come out of this terminal. Okay. Now I want to make you understand what is the direction of current. Let's think about the direction of current. Now electrons have gone from the emitter to the base. So from this terminal the electrons are going to go in. Correct? From this terminal the electrons are going to go in, which means that the direction of current is going to be out of the collector. So we call it IE or the IE or the emitter current. The current is going to come out of the emitter. So we call it IE or the emitter current. Okay. Now most of the electrons have come to the collector. So the electron is going to come out of this terminal. So the direction of current is going to be opposite. So it is called IC, or the collector current, and the collector current is going into the collector. And then some electrons are going to come out of the base. Okay, most electrons are going to the collector, but some electrons are going to come out of the base from this terminal. So the direction of current is going to be into the base, and this is called IB, or it is called the base current. Is this clear? Is this concept clear? Okay. So what is happening? Emitter base junction is forward biased, so electrons are injected into the base, and then base is thin, so most of the electrons pass through, and the base collector junction in reverse bias helps the process as well. Okay, so this is effectively what is happening, and what I want you to pay attention is what is the direction of these currents. What is the direction of emitter current? It is coming out of the emitter. What is the direction of the base current? It is going into the base. And what is the direction of collector current? It is going into the collector. Are you able to appreciate this? Think about it. Okay, Pratham is asking, sir, should I solve Irodov for JEE? Pratham, if you have done all the basic stuff, all the, whatever book you are following or whatever material you are following, if you are done with that, then you move on to Irodov. But in the objective pattern, I don't think you should spend much time on Irodov unless you have done everything else. Okay, if you have done everything else, then sure, go for Irodov, not a problem at all. It will certainly help you in JEE Advanced. All right. Okay. So I want you to compare these two diagrams and see if there are equivalent diagrams. Just check. Just check these two diagrams and tell me if they are equivalent diagrams. Okay. So this VEE. So this is the emitter, this is the base, this is the collector. Okay, so VEE is providing reverse forward bias to the emitter base junction, and VCC is providing the reverse bias to the collector base junction. Correct? Perfect. Now what I want you to focus is, let's talk about this junction. So IE is coming in, IB is going out, and IC is going out. Can you see that? And using Kirchhoff's law, we can say that IE will be equal to IB plus IC. Is this clear? IE will be equal to IB plus IC. You can apply that anywhere. Okay, you can apply this to the transistor as well. IE is the current coming out, and IC and IB are the currents which are going into the transistor, which means IE should be equal to IB plus IC using Kirchhoff's law. That's pretty straightforward, right? But what we have observed is that IB is much less than IE. Why? Because most of the charge carriers are flowing into the collector. Most of the charge carriers are flowing into the collector. So IC is going to be very close to IE, and IB is going to be very small. Okay, so IB is very small with respect to IE, and that is why and that is the whole point of creating a transistor like this. Okay, so typically IB is 1 to 5% of IE, and we are going to discuss how does that help. All right, now we define a few parameters which are going to help us understand this better, and we call them alpha and beta. Okay, so what is alpha? Alpha is IC divided by IE. What does it mean? That the fraction of current that goes into the collector compared to the emitter. Okay, so emitter current is getting divided into base and collector. So the fraction of the emitter current which goes into the collector is called alpha. And what is beta? Beta is IC upon IB. That how much times larger is the collector current greater than the base current. Correct? Okay, now if we use these two equations, we can very easily derive. Okay, I don't want to get into the derivation, that's pretty straightforward, that beta comes out to be alpha upon 1 minus alpha. Okay, beta comes out to be alpha upon 1 minus alpha. Now what happens over here? Think about this. Now alpha is generally of the order of 0.95. Okay, the collector and the emitter, the ratio of the collector current and emitter current is of the order of 0.95 to 0.99. Okay, which means that the collector current is going to be very high compared to the base current. Okay, so this term beta is of the order of 50 to 200. So the collector current is 50 to 200 times greater than the base current, and this is where the magic happens. Okay, this is where the magic happens. Beta is called the current gain. Beta is called the current gain. Okay, so what happens is IB is on the input side. Okay, IB is on the input side and IC is on the output side. I'm not saying they are input and output currents, that we are going to discuss later in this session, but I'm just saying that IB is on the input side and IC on the output side. So if we have even small current IB, then the current IC is going to be large, and this is basically what it means by current gain. Okay, this is what is meant by current gain. So even if we change IB slightly, the change in IC is going to be large. Okay, so that is why this term beta is very important, and its value is between 50 to 200. Okay, so I'm going to repeat myself. IB is on the input side and IC is on the output side. So for very small amount of IB, we get a very high amount of IC, and we are going to see how that is going to help us in voltage gain or signal gain. Is that correct? Okay, but I hope this is clear so far. Okay, now we define two kinds of beta. One is beta DC, which is simply IC upon IB. Okay, if the collector and base current are constant, they are DC, then we use beta DC, and we use beta AC, which is delta IC divided by delta IB. So if the current are variable, if we have a time varying source, in that case the change of collector current divided by change of base current will be called beta AC. And for all practical purposes, mostly beta DC and beta AC are almost same, so we can use them interchangeably. Is that correct? Okay, any problem over here? Any problem with the parameters? I hope this is clear. Okay, so this is of a lot of importance, the current gain. For very small amount of IB, we get a very high amount of IC. That's the whole point of the construction of a transistor. Okay, now we can use the transistor in three modes. It's called common emitter, common base, and common collector. So in this case, you can see that emitter is common between the base and the collector. Can you see that? And this is grounded. So this terminal and this terminal is connected through the battery, and this terminal and this terminal is connected through the battery. Okay, so what is common between them? The emitter is common between them, hence we call it the emitter, common emitter configuration. Similarly, if we ground this, the base is common over here. Here we call it the common base configuration, and here the collector is common, hence we call it the common collector configuration. Is that correct? But the most widely used configuration is the common emitter configuration. So all we have to understand or we have to study is the NPN junction in common emitter mode. That is what we need to study, because we need to study it as a device, and transistors are used as an amplifier and a switch. So they have to be operated. They are NPN junction, NPN transistors, and they operate in common emitter mode. Is that clear? Perfect. Okay. WB Gaming is asking what is the main work of base. Okay. So base, emitter and collector are working together to do something. Okay. The work of base is that most of the current or most of the electrons or most of the charge carriers that are coming from the emitter, it sends it to the collector. That is the work of base, so that the collector current is substantially higher than the base current. Okay, and when we see how it works as a device, then it is going to give us more clarity. All right, so now let's talk about the working of a transistor. Okay, so this diagram becomes very overwhelming if you look at it at the first point, in the first time. Okay, this becomes very complicated, looks very complicated, but I'm going to break it down for you. Don't worry. Okay, so for now I just want you to focus on this transistor. Okay, just focus on the transistor. So there is emitter, there is collector, there is base. Okay, emitter, collector, base, and this is an NPN transistor which you can see. Okay, so this is the transistor. Okay, now what we are doing is we are using this VBB to forward bias the base emitter junction. Can you see that? This positive connected to P side, okay, this positive terminal of the battery connected to P side and negative terminal of the battery connected to N side. Okay, so can you see that VBB is providing forward bias to the base emitter junction? Correct? Can you see that? Okay. Now what you also want to observe is that this battery VCC, this positive is connected to N and this negative is connected to P. Can you see that? Or this is connected to N, this is connected to N, but here I am going to explain it to you why this has to be higher in voltage. But just see that VCC, the positive terminal is connected to the collector and the negative terminal is connected to the emitter. Now what happens is that VCC is greater than VBB because our objective is to make the base emitter junction forward biased and the collector base junction to be reverse biased. We want to do that. Okay, so what we are going to do is we are going to ground this. Okay, so the emitter is at 0 volt. The emitter is at 0 volt. Now this is approximately 0.7 volt. Okay, I'm going to talk about it why it is 0.7 volt, but VBB is generally of the order of 0.7 volt, which means that the emitter is at 0 volt and the base is at 0.7 volt. Do you agree? Okay. Now VCC is much greater than VBB. VCC is of the order of 5 to 20 volt. Okay, which means the emitter is at 0 volt but the collector is at approximately, let's say, चलो मान लेते हैं 5 volt. ठीक है, let's keep the number low. The collector is at 5 volt. Is that correct? Okay, now you compare the collector and base. The collector is at a higher potential compared to the base, which means that the base collector junction is reverse biased, and that is the objective, to make the base emitter junction forward biased and the collector base junction reverse biased. That is why we use VCC, which provides the reverse bias to be very high. Okay, and that's what someone asked probably, and I said I'll answer now, and that is the reason this battery where the reverse biasing is happening, which is providing the reverse bias, it has to be greater than the battery which is producing the forward bias, because I want the base collector junction to be reverse biased. Is that correct? Alright, now after that we need to look at the currents. So this is the emitter current, it is coming out of the emitter. This is the base current, it is going into the base, and this is the collector current which is going into the collector. Is that correct? Okay, perfect. Now what we have done is we have attached a voltmeter which is going to measure the potential difference between the base and emitter, and we have connected another voltmeter which is going to measure the potential difference between the collector and the emitter. Okay, now these are just voltmeters. They are not going to be part of the circuit. They are not going to affect the circuit. They are just voltmeters. Okay, and then we have this resistance RB and RC to control the current. Okay, is this clear to everyone? Is the circuit for a transistor clear to everyone? Okay, unless it is clear, there is no point moving forward. So just let me know if this is clear to everyone. Okay, so we have the transistor in common emitter configuration, and then we have something called the transistor characteristics. So we want to look at the input characteristics and we want to look at the output characteristics. So input characteristic is basically the variation of IB, the base current, with VBE, and the output characteristic is the variation of IC, the collector current, with respect to the voltage, the potential difference, or VCE. Okay, so we are going to look at that. So let's look at the input characteristics. So in input characteristics, what we do is we make VCE constant. VC is not changing. Okay, the potential difference between the collector and emitter is not changing, it is fixed, and IB, the variation of IB on VBE is studied. Okay, and we get a graph something like this. Can anyone explain this graph to me? Can anyone just think why are we getting this kind of graph? And I'm sure you will be able to answer. Can you tell me why do we have this kind of a graph? So this is a IB and this is VBE. So we are looking at the variation of IB with respect to VBE, the potential difference between the base and emitter. So just think, why do we have this kind of a graph? Okay, the answer is here. Okay, so basically what is VBE? VBE is the potential difference between the emitter and the base, and the emitter base junction is forward biased. Okay, so if we are increasing VBE, we are basically increasing the forward bias voltage. Do you agree? Okay, we are increasing the forward bias voltage, and if we are increasing the forward bias voltage, what is going to happen? The electrons from here are going to flow into the base. Higher the forward bias voltage, okay, higher the forward bias voltage, more charge carriers are going to flow into the base. If more charge carriers are going to flow into the base, then higher is going to be the base current. Is that correct? Okay, and this is a typical PN junction. Okay, so this junction that we are seeing over here is a typical PN junction. Do you agree? It's a typical PN junction. Okay, so the characteristic or the variation of current is that of a forward bias current in a PN junction, isn't it? Okay, that's exactly a forward biased PN junction current. Okay, the only difference is that IB is in microampere because of the most of the current that is coming into the base, most of the electrons that are coming into the base, they're going to the collector. So very few electrons are coming out, hence the magnitude of IB is small, but the characteristic or the nature of IB is going to be that of a forward biased PN junction, and that's what we are seeing over here. Correct? Okay, so at around 0.7 or 0.8 volt, this is the cut-in voltage and this shoots up. Is this correct? Okay, so this is the variation of IB with VBE. Now what is output characteristic? In order to study the output characteristic, we keep IB fixed. Okay, we keep IB fixed. So we have chosen a value of IB, we keep it fixed, and we see the dependence of IC with VCE. Okay, what is VCE? This is VCE. So understand VCE as reverse bias voltage. Higher the value of VCE, higher would be the reverse bias between the collector and the base. Okay, think about it. Higher the value of VCE, higher will be the reverse bias voltage between the collector and the base. Okay, that's what we need to think about, and then we need to look at the variation. Okay, so we have drawn this graph for a fixed value of IB, and that value of IB is 10 microampere. Okay, it's a fixed value of IB. So what we see is that as we increase VCE, the collector current increases, but then it saturates. Can you see that? The collector current increases, but then it saturates. Think about it. Why does it happen? Think about it for a second. Okay, notice, or I'm going to say this again, what is VCE? VCE, higher is the VCE, higher is the reverse bias between the collector and the base. So let's try to understand this. So VCE is going to mean that the electric field here between the base collector junction is going to be like this. Okay, now if this is high, what is going to happen? All the electrons that are coming over here, the electric field is going to support the flow of electrons into the collector. Okay, so when VCE is 0, which means there is no reverse bias voltage, then what is going to happen? There is going to be no IC. So it will start with 0. But as we increase the reverse bias voltage, then the electric field also increases, and all the electrons that have come over here in the base are going to suck towards the collector because of this electric field. Okay, so the current, the collector current is going to increase, but after a point the collector current is going to saturate. Why is that going to happen? Because VCE is basically the appetite to get more and more charge carriers, okay? But what will be the actual charge carrier flow depend upon? It is going to depend upon the concentration and the geometry, okay? For example, I have an appetite to eat 10 chapatis, okay? My appetite to eat is 10 chapatis. So if you give me 10 chapatis, I'll happily eat 10 chapatis, okay? But if you give me 1 chapati, I'll eat 1 chapati. If you give me 2 chapati, I'm going to eat 2 chapati. If you give me 3, I'll eat 3. But the problem is you cannot give me more than 3. So even though my appetite is very high, even though VCE is high, which means that the appetite for high collector current is high, but what is happening? The collector current is still going to saturate. Why is going to saturate? Because there is a limit on the concentration of the charge carriers and the geometry. So because of the concentration of charge carriers and geometry, the collector current is going to saturate. Okay. So after a point, no matter how much you increase the VCE voltage, the collector current is going to be constant. Okay. Is that clear? Okay, and as we draw this graph for higher base current, obviously the collector current is going to be increasing. Okay, we know that very well because beta is equal to IC upon IB. So if we increase IB, then IC is also going to increase. Okay, so is this absolutely clear? The output characteristics of a transistor, is that clear? Alright, so now we talk about transistor as a device. Okay, we are going to talk about the transistor as a device. Okay, so here what I want to do is, I want to find a relationship between the voltages over here. Okay, so I'm going to go in this loop and I'm going to write the voltage. I'm going to go from here to here to here and to here. Okay, so I'm going to go in a clockwise sense. So this is going to become VBB. Notice I'm going from here to here. So this becomes VBB. Then I'm going in the direction of current. So this becomes minus IBRB. Okay. And then I'm crossing this. So what is this? This is the potential difference between the base and emitter. So just by using Kirchhoff's voltage law, I can write VBB minus IBRB is equal to VBE. Is that correct? Okay. So just remember this. VBB, or you can remember this, I'm going to write it as VBB is equal to VBE plus IBRB. Is this clear? And I'm going to do the same thing in this circuit. Okay, I'm going to do the same thing in this circuit and I'm going to start over here. Okay, so here what I'm going to get? I'm going to get VCC going from across this battery. I'm going to get VCC. Then I'm going to get minus ICRC and this will be equal to VCE. So what do we have? We have VCE is equal to VCC minus ICRC. So simply what I have done is that I have written KVL for these two loops and I have found the relationship between these parameters. Hyper Gaming is asking where the graph is going in parallel to VCE axis, that time the value is 0.95 approx. It can, so if you are talking about this value, are you talking about this value? So it will depend on the geometry of the transistor, the material of the transistor, the doping level of the transistor. It is going to depend upon that. But we are not worried about the values right now. We are mostly worried about, or we are concerned with the nature of the graph. Okay, the values would be different in different scenarios, but we are concerned with the nature of the graph. Okay, perfect. Okay, Sakshi is asking, sir, please explain alpha and beta parameter of transistor current. Sakshi, I have done that in this session itself. So when the session ends, you can go back and you can watch that explanation again. Okay. All right. So we have this relationship between VBB and VCE. Now what we are going to do is this VBB will be called the input voltage. Okay, so this, the potential difference VBB, I'm going to say this is the input voltage. I'm going to use that as an input voltage. So any signal, any appliance I'm attaching to give the, so any input that I'm attaching, that is simply going to be VBB. Is that correct? Okay. And VCE is going to be the output voltage. So any appliance I have to work, any output I have to gain, that is going to come between VBE. Okay, that is going to be CE. That is going to be between C and E. Can you see that? Okay, so this is input. Input is simply VBB. And what is output? Output is the voltage between the collector and the emitter. So any output that I have to get, I'm going to get it between the collector and the emitter. Is this clear? Alright, so I'm going to write it over here. And now what we need to do is, we need to understand that as Vi changes, what happens to VO? This is called transfer characteristics. That as Vi changes, what happens to VO? So I'm going to make a table which is going to explain everything. So this is Vi, then there is going to be VBE, then there is going to be IB, then there is going to be IC, and then there is going to be output. Okay, let's try to understand this. Okay, what is input voltage? Input voltage is VBB. Let's say Vi is 0. So what will be the input voltage? The input voltage is going to be 0. Okay, input voltage is nothing but VBB. So let's say the input voltage is 0. Now if the input voltage is 0, what is going to happen to VBE? VBE is the voltage between the base and the emitter, correct? It is the voltage between the base and the emitter. And what is this doing? This is providing forward bias to base and emitter. Now if VBE is 0, then the forward bias between the base and emitter is going to be 0. Okay, so VBE is going to become 0. And what will happen to IB? Because the forward bias between the base and emitter is not there. Okay, the voltage VBE is 0. So in that case, what is going to happen? That there is going to be no base current. Okay, can you see that? There is going to be no base current, because only when the base emitter junction is forward biased, there is going to be any current, there is going to be any charge flow that is going to happen. So what will happen to IB? IB is going to be 0. And if IB is 0, what is going to happen to IC? So we know that IC upon IB is equal to beta. Now if there is no charge flowing from the emitter to the base, there will also be no charge flowing from the base to the collector. Okay, so IC is also going to be 0. And if IC is going to be 0, just look at this equation. If IC is going to be 0, the output voltage is going to be how much? The output voltage is going to be VCC, and that is going to be the maximum output voltage. Is this clear? Any problem over here? Clear? Perfect. Now what we are going to do is we are going to increase Vi. Matlab we are increasing this battery voltage VBB. We are increasing VBB. Okay? If we are increasing VBB, then what is going to happen? This is providing forward bias to the base emitter junction. It is providing forward bias to the base emitter junction. Then the forward bias voltage between the base emitter is going to increase. If the forward bias voltage between the base emitter is going to increase, then the base current is also going to increase, because now the charge carriers are going to flow from the emitter to the base. So IB is also going to increase. Now if IB is increasing, IC is also going to increase. And if IC is increasing, what will happen to VO? Just look at this. If IC is increasing, what is going to happen to VO? VO is going to decrease. Okay, if IC increases, we are subtracting a larger quantity, so VO is going to decrease. Is that correct? So as we increase the input voltage, the output voltage is going to decrease. And when, let's say, the input current becomes very high, okay, the input voltage becomes very high, then the forward bias voltage is also going to be high. If the forward bias voltage is high, then the base current is also going to be high. If the base current is high, in that case, the collector current is also going to be high, but it is also going to get saturated. Okay, as IB increases, IC also increases, but IC is going to get saturated. Think about it. If IC is increasing, then VO is decreasing. As IC is increasing, VO is decreasing. Okay, and what is VO? VO is providing reverse bias. Is that correct? Okay, so VCC over here is providing the reverse bias. So in this case, what is happening? As IC is increasing, the reverse bias voltage is decreasing. And if the reverse bias voltage is decreasing, its appetite to get more and more collector current is also decreasing. Okay, so what is going to happen? The collector current is going to become high, and after that point, it is going to get saturated. Okay, now if collector current becomes very high, we can see from this equation that VO is going to become very low or even negligible, even close to zero, and it is going to saturate as well. Is this clear? Is this clear to everyone, this scenario? We start with 0, we increase the input voltage, and we see that what is going to happen at a high input voltage. So what is there to notice? That at a high input voltage, the collector current is going to be high and get saturated, and the output voltage is going to be very low and it is going to become saturated. Okay, so all of this we can neatly put on this diagram. Okay, you could have seen that. We can put this on this diagram. So when the voltage is low, what is happening to IC? IC is low, which means the output voltage is high. Can you see that? This is called the cutoff region. Why is it cutoff region? Because IC is going to be nearly equal to 0. Cutoff means IC. So cutoff region or saturation region, we are talking in terms of IC. So when the input voltage is very low, the output voltage is going to be high, and the collector current is nearly going to be equal to 0. We call it the cutoff region. Okay, and when the input voltage is high, then IC becomes saturated. Can you see that? IC becomes saturated. That is why we call it the saturation region. And what happens to the output voltage? The output voltage becomes very, very low or negligible. Is that correct? And in between them, we have the active region. Okay, so it's very simple. So what is the crux of all of this? That when input voltage is low, the output voltage is high, and when output voltage is high, when input voltage is low, the output voltage is high, and when input voltage is high, the output voltage is low. This is the crux of our discussion. Is that correct? Right? Okay, now what happens because of this? Because of this, we can use it as a switch. Okay, we can use it as a switch. So what is happening? I am keeping the input voltage low. Okay, I am keeping the input voltage low. In that case, the output voltage is going to be high, and I am going to receive the output from here. So what I have done is I have connected this bulb to the output. Now if the input voltage is low, then the current in the collector is going to be 0, which means that the transistor is going to become off. And if the transistor is on, the output voltage is high, and this bulb is going to glow, and this bulb is going to be in the on state. Can you see that? Can you see that? Okay, so if we are keeping the input voltage low, the transistor would be shut off, but the bulb is going to be getting a high voltage. Okay, or the output voltage is going to be high, hence it is going to be on. Correct? Now if we take the opposite case, what is going to happen? Now if we take a voltage which is greater than this value, if the input voltage is high, then collector current is going to be high, so this transistor is going to be on, but the output voltage is going to be very close to 0, so the bulb is going to become off. So just by switching the voltage between this region and this region, what we are doing is we can switch on or off the transistor. Okay, that is how we can use it as a switch. Is that correct? Any problem over here? Okay, so this is the way we use it as a switch. Now there's another use of transistor where we use it as an amplifier. Okay, so if there is an input signal, the transistor can amplify the signal, meaning it can make the amplitude greater. Okay, and how do we achieve that? It's very simple. The same idea over here. Okay, now let's say if you are increasing the input voltage. Okay, let's say this is delta Vi. You are increasing the input voltage. Okay, then in that case, what is going to happen? There is going to be a change in the output voltage as well. Okay, and what you observe here is that if the change in input voltage is positive, the change in output voltage is negative. Can you see that? And this is what we call the voltage gain. Okay, this is what we call the voltage gain. This is delta V output divided by delta V input. Okay, so if we change the input voltage by a small amount, the output voltage is going to change by a large amount. Okay, because this slope is going to be very, very high. Okay, so if we change the input voltage, the output voltage is also going to change, and it is going to change by many times. Okay, this is what is called the voltage gain. Similarly, if we decrease the input voltage, the output voltage is going to increase. Okay, and it is going to increase by many times. Now, this is the idea behind the amplifier, and I'm not going to go into the derivation. You can look at the derivation from any book. Okay, I don't have that much time to look into the derivation, but if we do the derivation, okay, if we do the derivation, it's a very simple derivation. What we are going to see is that the voltage gain comes out to be delta IC divided by delta IB into RC divided by RB. Okay, and what is delta IC upon delta IB? And we'll have a negative sign also, because if the input voltage increases, the output voltage decreases, and vice versa. So there's going to be a negative sign also. So what is delta IC upon delta IB? It is called beta AC. We have seen that delta IC upon delta IB is called beta AC, and then multiplied by RC by RB. Now, what is voltage gain? The voltage gain depends on beta AC, and we know that beta is in the range of 50 to 200. So for small change in the input voltage, the change in the output voltage is going to be high, and that is why the signal is going to be amplified. The change in output voltage is going to be amplified. Okay, so we should remember this voltage gain. And also the power gain is given by the current gain into the voltage gain. So you can simply multiply it by beta, and you are going to get the power gain. Okay, so this is the idea behind the transistor acting as an amplifier. Okay, we get a voltage gain. Is that correct? Right? Alright, so this is the end of this session. I hope this session was helpful for you to understand semiconductors, the basics of semiconductors, the important topics of semiconductors and transistors. Okay, the only thing I have not done in transistors is the derivation because of the lack of time, but I have explained to you the concept that are involved in the transistor, which are important. Okay, if you understand the nature of input and output voltage, you are going to understand everything about transistors. All right, so that is it, folks. I hope this is clear. This is helpful. Thanks a lot for joining this session, and very soon I'm going to see you in another session. But till then, keep practicing, keep getting better, and have fun with learning. Thanks for watching.